In the last video, we introduced spin states, operators, the Bloch sphere, and Pauli matrices. Now, we'll connect that to measurements in quantum mechanics. Because in quantum mechanics, measurement isn't just looking at something and reading off whatever value it has. Measurement has structure that is built on operators, eigenvalues, and expectation values. We'll begin by quickly reminding ourselves what an operator is. Operators are mathematical objects that act on a state. For spin 1/2 systems, our states are two component vectors, so our operators are naturally 2x2 matrices. The state tells us how the spin is represented, while the operator tells us the question that we're asking about the state or what action we're applying to it. And this distinction is really important. Applying an operator to a state is not always the same thing as getting a measured value. Sometimes applying an operator changes the state, and sometimes the state comes back unchanged except for a number in the front. This second case is what we'll look at. This is the case where eigenvalues come in. But before we go further, we need to clearly define what we mean by state in quantum mechanics. Dirac notation, or Bra-Ket notation, is a pretty neat mathematical language that we can use to represent states in quantum mechanics, formulated by Paul Dirac. A state written as a ket looks like this, and this is just a column vector. For a spin 1/2 system, it looks like this, where the coefficients of C alpha and C beta can be complex numbers. Now, every ket has a corresponding bra written this way. We get the bra by taking the transpose of the ket and then taking the complex conjugate of every element. So if the ket looked like this column vector here, then the bra would look like this row vector. The operation we use to go from ket to bra is called Hermitian conjugation, which is just the transposing plus the complex conjugation. Transposing means that we swap the row and the column elements with each other. For example, transposing this 2x2 matrix will give us this new matrix, and transposing this 3x3 matrix will give us this new matrix. Now, complex conjugates apply to numbers that contain an imaginary term I. Complex numbers can be written as a sum of their real and imaginary parts. The complex conjugate of a number is obtained by changing the sign of the imaginary part. So simply, if we have I, we just replace the I with negative I. For example, we have 3 plus 2i, and that will become 3 minus 2i. This is essential because probabilities and measurable quantities must be real numbers, even though the coefficients themselves can be complex. Now, another good question is, why do operators act on kets and not bras? Operators act on the states or matrices to the right of it, and you will always see the ket to the right of an operator, never a bra. This is because of the rules of matrix multiplication. An operator is a matrix, and a ket is a column vector. So we can multiply A times the ket of psi only because the inner indices match. The number of columns in the first matrix has to match the number of rows in the second matrix. But a bra is a row vector, so multiplying an operator on it would not have the right dimensions. Instead, the bra multiplies from the left. This ensures that the inner dimensions match. Now let's understand this using spin. For a spin 1/2 nucleus, one of the most important operators is the z-spin angular momentum operator, Iz. In units of h bar, we can write it as so. And our two basis states are going to be alpha and beta. Now let's apply Iz to alpha. Iz times the ket of alpha is just going to give us 1/2 times this column vector of 1, 0, which is just 1/2 times alpha. This is an eigenvalue equation. The operator acted on the state, but the state itself did not change into a new direction. It came back as alpha again, but just multiplied by a number. And that number is the eigenvalue. So alpha is an eigenstate of Iz, and its eigenvalue is plus 1/2. If we include the units of angular momentum, the measurement value is plus h bar over 2. Now let's do the same thing with beta. Iz times the ket of beta is going to give us negative 1/2 times the column vector of 0, 1, which is just negative 1/2 times beta. So beta is just an eigenstate of Iz as well, but its eigenvalue is negative 1/2. And with units, the measurement value is negative h bar over 2. This is the cleanest example of what measurement means in quantum mechanics. If the state is an eigenstate of an operator you are measuring, then the measurement gives the corresponding eigenvalue. We can also see why it does this by understanding why the Iz operator looks the way it looks in the first place. And that's because we're using the basis of alpha and beta. If it helps, you can look at the matrix like this now. When I feed this operator an alpha, it's going to give me back an alpha, but no beta. When I feed a beta to it, I'm going to get no alpha, but I'm going to get a beta that's negative. And that 1/2 gets multiplied throughout as well. You can also see the other operators like this as well. Now let's look at a more general state. Any spin state can be written as a linear combination of basis states. So for this full state psi, it can be written as a combination of many basis states with their probability amplitudes. For spin 1/2, we only have two basis states of alpha and beta, so this is going to become this equation right here. And the probability of measuring a particular basis state is just the squared magnitude of its probability amplitude. Now, the summation form also gives us a great place to introduce the important idea of overlap. When we write a general state like this, we're saying that the state is built from a collection of basis states. But if we want to know how much one particular basis state is present in psi, we need a way to extract that component. This is what the inner product does. So if I take the overlap between one basis state, psi m, and the full state, psi, I can write it as this full summation right here. The inner product is that term at the end that tells us how similar those two basis states are. If they're the same state, then the overlap is 1, and if they're different orthogonal states, then the overlap is 0. So for an orthonormal basis, this simplifies to a Kronecker delta. Orthonormal means that every vector in the space you're working with is going to satisfy these two criteria. That every basis is orthogonal to each other, meaning that they don't overlap, and that each basis is normalized, meaning that they have a length of 1. The symbol delta is the Kronecker delta, and it equals 1 when m is equal to n, and 0 whenever m is not equal to n. So basically, the Kronecker delta is a mathematical way of saying the same state gives 1 and different orthogonal states give 0. So for spins of 1/2, this means that the inner product of alpha and alpha is 1, and beta's inner product is also 1. But the inner product of alpha and beta is 0, and the inner product of beta and alpha is also 0. Because alpha and beta are orthogonal basis states. They have completely distinct directions in this two-dimensional spin state space. Now let me show you why this is useful. If we have this general state right here and we want to extract the alpha component, we can take its overlap with alpha. So the inner product of alpha and psi. Substituting that into the equation for psi gives us this. And then we can distribute the broad terms across. And look at this. We know that the inner product of alpha and alpha is 1, and the inner product of alpha and beta is 0. So this means that the inner product of alpha and psi is just going to give us C alpha. The overlap with alpha pulls out the alpha coefficient. In the same way, if we did this with beta, then the inner product of beta and psi would just do the same thing, pull out the coefficient of beta. So the inner product is how we project a state onto a basis direction and ask how much of this basis state is inside the full state. And once we have that coefficient, the probability can come from its squared magnitude. This idea is going to show up everywhere. When we measure spin along the z, we're going to ask how much of a state overlaps with the eigenstates of Iz. If the state overlaps strongly with alpha, we're going to be more likely to measure plus h bar over 2. And if it overlaps strongly with beta, we're going to be more likely to measure negative h bar over 2. And if it overlaps equally with both, like the plus x state does, then a z measurement will give us alpha half the time and beta half the time. Okay, now we can talk about expectation values. An expectation value is the average result you would get if you repeated the same measurement many times on identically prepared systems. So if I prepare the same spin state over and over again, measure the same observable over and over again, and then average all those results, that average is the expectation value. For an operator A, we can write the expectation value as this, where the operator is sandwiched in between the bra and the ket. At first, this notation can look a little mysterious, but it's really saying three things. First, we have the ket of psi, and then the operator acts on that state. And finally, we take the overlap of the result with the original state using the bra of psi. So the expectation value is not just apply the operator, it's apply the operator and then compare the result back to the original state. Now let's expand this using the summation form. We've agreed that we can write the ket of a state using this form right here, where the state is built from basis states, each with some coefficient Cn. And its corresponding bra looks like this right here. Now, you might wonder why I switch from n to m in the indices. The reason is that the bra and the ket are separate sums. The ket sum runs over all the basis states on the right side, and the bra sum also runs over all the basis states, but on the left side. Those two sums are independent. So the bra could be referring to basis state 1, while the ket could be referring to basis state 2. Or the bra could be basis state 3, while the ket is basis state 9. Or they could just be the same basis state, 1 and 1. Every possible pair is included. That is why we use two indices, m for the bra side and n for the ket side. So when we plug in both expansions into the expectation value formula, we get this large equation right here. And multiplying those sums gives us one double summation. This expression shows that the expectation value is built from all combinations of basis states weighted by their amplitude. The term at the end is called a matrix element. It tells us how operator A connects basis state psi n to basis state psi m. So if m and n are different, that term is asking whether the operator connects two different basis states. And if m and n are the same, it's now asking about the contribution from the same basis state. Now this general expression is powerful, but it can also look scary. Luckily, it becomes much simpler when our basis states are eigenstates of the operator that we're measuring. If psi n is an eigenstate of A, then A operating on psi n will just produce an eigenvalue in the front and return the same state. This means that the operator does not turn psi n into some new mixture of states, but it just gives back the same state multiplied by its eigenvalue, lambda n. So inside the expectation value, we can write that in. And since lambda is just a number, we can pull it out to the front. And now orthogonality does the work for us. Because if the basis is orthonormal, then we can say that this inner product is equal to the Kronecker delta. So now we have this equation. The Kronecker delta kills every term where m and n are different. So all the off-diagonal terms are going to disappear. Only the terms where m and n are equal survive. That collapses the double sum into a single sum. And since Cn star times Cn is just equal to the magnitude of Cn squared, we can get this fully simplified form right here. This equation says that the expectation value is the sum of each possible measurement value, lambda n, weighted by Cn squared, which is the probability of getting that value. So expectation values are basically weighted averages. The eigenvalues are possible measurement results, the squared amplitudes are probabilities, and the expectation value is the average result. So for spin 1/2, we're lucky because we only have two basis states, alpha and beta. And for Iz, alpha and beta are eigenstates, so we get lucky once more. The expectation value of Iz for the equation of psi that we've been using is this form right here. And we can simplify that to 1/2 times the difference between the squared amplitudes of alpha and beta. Now let's derive this from matrix multiplication. Again, we'll start with this general superposition state of psi, with C alpha times the ket of alpha and C beta times the ket of beta. In matrix form, using the alpha beta basis, this becomes this 2x1 column vector of C alpha and C beta, and its corresponding bra is the complex conjugate transpose, which looks like this, and in matrix form is a row vector of C alpha star and C beta star. And the Iz operator in units of h bar looks like this as well. Actually, I'll show you how to get the expectation value in two ways. First, we'll do it by brute force matrix multiplication, and second by using what we know about orthonormality and eigenvalues. So in the first way, we apply the matrix of Iz to the ket of psi, and here we just multiply the rows by the columns. This will give us 1/2 times the 2x1 column vector of C alpha and negative C beta. And this is only the first part of getting to the expectation value because we've applied the operator to the ket, and now we're just left with applying the bra from the left side. The expectation value is this sandwiched formula right here, and we already found that applying Iz to the ket of psi will give us this 2x1 column vector. So now we insert the bra to the left. Here we can pull out that 1/2 to the front, and then we can again just multiply row by column. And since we just multiplied a 1/2 with a 2/1, the result will be a 1/1 scalar value. And a complex number times its complex conjugate will just give us its squared magnitude, so we can get that final form right here. So brute force matrix multiplication gives us exactly what we expected. Okay, now let's do it the second way. In state language, we already know what the Iz operator does to the basis states. If we apply Iz to alpha, we'll just get a 1/2 in front of alpha, and if we apply it to beta, we'll just get a negative 1/2 in front of beta. So now let's apply that to the full state of psi. Applying Iz to psi means that we're just applying Iz to the superposition of alpha and beta, and here we can just distribute the operator to both. Now, using what we know about the eigenvalue relationships we just mentioned, we'll just have a 1/2 in front of alpha and a negative 1/2 in front of beta. So right now we can get 1/2 C alpha times the ket of alpha minus 1/2 C beta times the ket of beta. So now we take this result of Iz operating on psi and multiply it from the left by the bra of psi. And then from this, we can distribute everything to get this really long form. And now using what we know about orthonormality, we can say that the inner product of alpha and alpha is 1, alpha and beta gives 0, beta and alpha gives 0, and beta will give us 1. So the cross terms will disappear. And again, a complex number times its complex conjugate will give its squared magnitude. So from that, we can get that final form that we saw before. So the Bra-Operator-Ket expression is just a really neat way of computing a weighted average. Multiplying all three gives us one number, and in this case, that number is the average z component of spin in units of h bar. Now, interestingly enough, we can connect this directly to the Bloch sphere. In the last video, we said that a general spin state on the Bloch sphere can be represented as this. Doing the same math that we just did for the Iz expectation value of this other psi equation, we can also do it for this psi equation and get these following expectation values. For Iz, it'll be 1/2 cosine theta. For Ix, it's 1/2 sine theta cosine phi. And for Iy, it's 1/2 sine theta sine phi. This is pretty nice because now we can just sneak past multiplying matrices and using that sandwich formula when we want to calculate expectation values. Anyway, these expectation value formulas correspond directly to the coordinates of the Bloch sphere. So the Bloch sphere is not just a picture, but it's a map of expectation values. Let's test this with the positive x state. Theta would be 90 and phi would be 0. So for this state, Iz's expectation value would be 0, Ix would be 1/2, and Iy would be 0. Even though a measurement of Iz is supposed to give us either plus or minus h bar over 2, the average is 0. And this makes perfect sense because since we're getting both the positive and the negative with equal probabilities in individual measurements, it makes sense because it would average to 0. This shows us that a state can be definite along one axis and uncertain along another. Now, connecting this back to NMR again, we're not observing single measurements. We're observing an ensemble of spins. So what we detect is directly related to expectation values. Iz corresponds to longitudinal magnetization, and Ix and Iy correspond to transverse magnetization. These expectation values add up across many spins to produce a measurable signal, and that's the bridge to what we're going to need to move on forward. Eigenvalues describe individual measurement outcomes, and while expectation values describe averages over many systems. And NMR measures those averages.